Hello and welcome to the Daily Space for today, Friday, January 15th, 2021. I am your host, Dr. Pamela Gay, and I am here to put science in your brain. This show marks the end of our second week of recording what we hope will be a constantly improving show for you to watch here on Now Media that we record live in front of an audience on twitch.tv/CosmoQuestX. This show is put together by a tiny team who are learning as fast as we can. We are so grateful for all of you who have been here. And if you like what you see, we hope you'll let people know about our little show. You can catch us here, but we also put out a podcast edition that includes unedited interviews and longer versions of some of our stories. You can find The Daily Space on iTunes, Spotify, Google Play, and wherever else you listen to podcasts. We hate to admit you've seen a few typos, and we're still learning how to bring you the best graphics we can. But our goal is to bring you better content every week as we bring you all that is new in space and astronomy. And this includes bringing you content about our own special planet, Earth. Change happens. You can look around our world and see the impact of both natural processes and human activity. Storms cause landslides and even forest fires, which change the structure of the landscape. People dig out dirt and plant to build structures, which can lead to more problems from the storms. Wind, rain, freezing, melting, volcanoes, earthquakes. So many processes affect the world around us, both on the large and the small scale, and we struggle to track them. Which is why it's amazing that scientists have determined that the arrival of Europeans in North America led to an increase in the erosion rate and the rate of river sediment accumulation by a factor of 10. An international team analyzed 40,000 years of sediment at 126 sites across the continent to find the natural background rate of erosion. Then they compared those values to the rate from the past 200 years. Humans moved as much material in the past century as would have naturally happened over 700 to 3,000 years. The work was published last year in Nature Communications, and lead author David Kemp noted, by having this huge compilation of data that stretches back many thousands of years, we're able to contextualize the human impact against that natural geologic variability. It was a surprise to me that the jump was there and that it seemed to be so neatly coincident with European arrival. You might think the effects would be limited to the east coast of North America, where the first of the European colonists set up shop, so to speak. But the study shows that the impact on the sedimentation rate is seen across the continent. Europeans brought their own techniques for agriculture, animal husbandry, and river management, and literally changed the world around them. Of course, conservation efforts have the challenge of working against these massive changes to try and restore habitats to a more natural condition. The study notes there is good news in that sedimentation rates have been reduced in the last few decades due to those efforts. We as a planet need to do a better job of listening to our planet. No, really, we need to listen to our planet. And that is what researchers have done in new work presented in the journal Geophysical Research Letters. Researchers listened to rocks by attaching sensors to boulders and monitoring the cracking noises they made due to weathering. They measured any resulting cracks and found that the higher rates of fracture growth happened in higher temperatures and wetter air. Not a good sign when we already know we're dealing with higher temps and bigger storms. I always think of Doctor Who when we talk about rock erosion. Water always wins. On top of accelerated weathering rates, breaking rocks can release carbon into rivers and oceans. Just what we need, right? And these results aren't due to huge noticeable cracks in rocks. They come from a process known as subcritical cracking. Lead author Missy Eppies writes, subcritical cracking is analogous to the weeks-long growth of a crack on a car windshield, as opposed to the rapid cracking that occurs if you hit the same windshield with a hammer. The crack grows slowly and steadily, with very low forces being applied to that crack. The team intends to expand their research to more types of rocks, and we'll update you when they have more results. Another result of our wetter atmosphere is a loss of coastal land. Coastlines are fickle to begin with, impacted by wind and wave and even glaciers. Take Cape Cod, for example. During the last ice age, the Laurentide ice sheet covered North America from eastern Canada down through New England, ending at what we now know as the outer lands. As the ice advanced and later retreated, it moved sediment and left behind glacial deposits. The landscape ended up malleable and pockmarked with kettle ponds that became cranberry bogs of today. Cape Cod was free of ice only 18,000 years ago, the blink of an eye, geologically speaking. Cape Cod was also home to megafauna like mammoths, as well as the indigenous people that hunted them. But as the ice retreated, it also melted and the sea levels rose bit by bit, moving people and animals further inland. The currents around the shore changed, and the spit of land that forms the hook of the cape formed as sand was moved in new directions. Provincetown, a fishing village that is home to 3,000 residents and a huge tourist destination during the summer, that's where it was built. But now the sea levels are rising again and alarmingly. They have risen by 28 centimeters since 1922 and are expected to rise to 3 meters by the year 2100. Flooding events are already on the rise, and a huge nor'easter in 2018 inundated parts of the town. The airport could easily be impacted. Town planners are trying their best to shore up, well, the shore by moving sand from the hook to the town. Other parts of the Cape are being left alone to let nature take its course. No one is certain how long that will take. The highest point is only 49 meters in elevation. Some of the lowest points are at 8 meters. And with all the uncertainties in climate models, estimates of the timeline for overtopping the Cape are vague at best. Climate change is real, and it's impacting real people now. There is one small silver lining in climate change. One particular species of truffle, the perigord, looks like it will thrive in wetter, warmer conditions. In new research published in the journal Scientific Reports, researchers, they report the results of their research into just how several varieties will respond to climate change. And perigord is going to do really, really well. Plant now, though, everyone. It takes 5 to 15 years to establish a truffle orchard and to harvest actual truffles. After the break, we'll return to our usual astrophysics, this week continuing to come to us from the American Astronomical Society meeting. In math and physics, there are few problems as annoying as the so-called three-body problem. When three objects are gravitationally pulled together in space, they often interact in chaotic ways that can't be predicted with straightforward equations. Unfortunately, the universe doesn't care what math is easy or hard for us to do, and it is going to do what it is going to do, and one of the things it is going to do is periodically give us three supermassive black holes that are interacting as galaxies merge. This isn't a common event, but it's an important one for astronomers to try and understand if we want to build a model for how massive galaxies have formed over time. In work presented at this week's American Astronomical Society conference, Stanford University's Addie Ford presented results of combing through myriad catalogs of galaxy images taken in optical, infrared, and X-ray light to find triple systems. It turns out that triple mergers are exceedingly rare, with only 7 mergers of larger systems being found in current survey data. And in all of these cases, these central black holes were found within 30,000 light years of one another. 7 isn't a lot of data, but it is enough to see that these systems are highly varied. One of the seven had only one of its three black holes actively consuming dust and gas pushed in by the merger. One had no black holes actively feeding, none. Most commonly, in four of the seven, two black holes were active, and in just one system, all three black holes were feeding. These results help us understand the full range of ways supermassive black holes can draw material and energy toward one another. A simple pair of supermassive black holes is theorized to have trouble shedding enough energy to allow two monsters to merge. But it's thought that with a third black hole, that third black hole may be able to help redistribute that energy and make a merger possible. These results seem to hint that anything is possible. The definitive can they, can't they of supermassive black hole mergers is ultimately going to be seeing one in action. The planned LISA mission may someday be able to detect the gravitational waves of supermassive black holes if they occur. Let's hope triple mergers aren't required. But if they are, it looks like they just might be able to do pretty much anything. Black holes eat stars. We know this. We've managed to catch it happening. And now we've managed to find a star that is regularly flaring up as it swoops by its black hole. It is so regular, in fact, that it's being called Old Faithful as it flashes every 114 days like clockwork. In new work also presented at the AAS meeting and soon to be published in the Astrophysical Journal, scientists used data from NASA's Swift Observatory and TESS spacecraft and the telescopes in the All-Sky Automated Survey for Supernova Network, or ASSASSIN, to observe the star and its regular flashes of light. The object, now called ASSASSIN 14Ko, resides in our southern skies in a galaxy about 570 million light years away. The first flare was detected back in 2014, and it was thought to be a supernova. Then lead author Anna Payne went back through the data in 2020 and found 17 flares, all 114 days apart. This type of a regular flare had never been seen before. So the team predicted that the galaxy would flare on May 17, 2020, and joint observations were coordinated, and voila, the flare happened right on schedule. It was followed by two more predicted and observed flares in September and December of last year. Basically, there is a star orbiting its galaxy that passes close enough to its black hole every 114 days to cause a flare as matter is pulled from the star and bursts with energy. The black hole is estimated to be 20 times the mass of our own Milky Way galaxy's Sag A star supermassive black hole. And one of the co-leads of the ASSASSIN project says there's even evidence of a second supermassive black hole in this galaxy. Co-author Chris Stanek summed the work as, in general, we really want to understand the properties of these black holes and how they grow. It gives us a truly unique opportunity to better understand the phenomena of episodic mass accretion on supermassive black holes. The ability to exactly predict the timing of the next episode allows us to take data that we could not otherwise take, and we are taking such data already. I'm sure we'll hear more about this work in the coming months. In our final story before we go to commercial, we'd like to let you know about a new alternative energy source that I really don't think anyone should take advantage of. In a new paper appearing in the Physical Review D, physicists Luca Camiso and Filippi Angeno describe how energy can be extracted from black holes. According to Camiso, our theory shows that when magnetic field lines disconnect and reconnect in just the right way, they can accelerate plasma particles to negative energies, and large amounts of black hole energy can be extracted. When I first encountered this article, I assumed their discussion of energy extraction was relevant for how energy moves through systems that involve black holes, and that this research would allow us to better understand things like how black holes spin and how this transfer of energy might drive known phenomenon like jets of high energy particles. And it does do all that. What I wasn't expecting was Camiso's claim that this energy could be harnessed by advanced civilizations. To be fair, a society that lived near a black hole and harnessed its energy could live in their own slow pocket of time, and that has a certain appeal. Nevertheless, this just strikes me as a bad idea, but I'm just a scientist. This research is the kind that This research is the kind that just needs a science fiction writer to weave it into a new tale of other worlds. It's really hard in astronomy to know if we really understand what's happening to a star hundreds or thousands of light years away that will live for billions of years. The best we can really do is try and create computer models that can replicate what we see. In many ways, our ability to understand the universe is limited by the computational power we can access. One of the hardest to understand objects in our universe is the planetary nebula. These ghostly relics of former stars come in a myriad of shapes and have highly detailed geometries. Some are simple bubbles, and these make sense as the puffed off atmosphere exhaled in the final breaths of a star like our sun. Other systems, however, present us with crazy boxes and other weirdnesses that are baffling. To try and understand what might be happening, researcher Segev Shabir of Louisiana State University simulated the final evolution of a red giant star with a lower mass companion. Most stars in our universe aren't alone, and stars regularly gravitationally interact. In his models, Shabir considered what would happen if a small companion star had jets. When a star cannibalistically strips material from a neighbor, that in-spiraling material can generate jets of material that point out the star's poles. By adding this extra bit of physics to his computer software, Shabir was able to replicate the stripping of a star's atmosphere and visualize amazing geometries reminiscent of what we see. This work still has a ways to go, but it appears to be going in the right direction, and it is a beautiful direction at that. One of the most frustrating things about astronomy is that most of the things we're interested in don't change on human timescales or even humanity length timescales. Planets form over hundreds of thousands of years, galaxies merge over billions of years. Things generally don't change such that we can see them. There are explosive exceptions, however. Supernova can go off in moments and generate nebulae that we can see expanding across years. Recently, a team of astronomers using the Hubble Space Telescope imaged a ghostly nebula in the nearby Small Magellanic Cloud. This is a supernova remnant with the uninspired name 1E0102.2-7219. This object was imaged twice by Hubble, with the two datasets being taken 10 years apart. Careful analysis of the tadpole-shaped knots of glowing gas around this supernova remnant revealed their slow motion across the sky. Working backwards, researchers John Banovitz and Danny Mislavojevic were able to estimate the supernova's initial explosion could have been roughly 1,700 years ago, visible during the Roman Empire, but not to the Roman Empire because it was visible in the southern hemisphere. Unfortunately, this object's southern location means it was probably seen, but not by a culture that has left us written records we can look through. Supernova like this should produce a neutron star when they go off. And this neutron star can be seen rocketing out of the explosion like a cannonball. This team used their Hubble data to try and find where that neutron star ended up. They're not sure if they found it or found a knot of glowing gas masquerading as a neutron star. If they did find it, the neutron star would have been the fastest so far recorded and would have been moving at an amazing 2 million miles per hour. More observations are needed, and when they are published, we'll bring them to you right here on the Daily Space. Our final story of the day brings a new view on a galaxy that is an old favorite to many amateur astronomers, the Whirlpool Nebula, or M51. While the image we're showing may look like it was made from some new Photoshop or Instagram filter, it's actually a combination of a Hubble image and magnetic field data taken with the Sophia Airborne Observatory. Using its own style of polarized glasses, Sophia is able to see how magnetic fields twist through the galaxy. To the surprise of the observers and adding to the beauty of this image, these lines become more chaotic the farther one looks from the center of the galaxy. Now, I kind of want a magnetic field filter for Instagram, but I'm not sure I can afford a camera like Sophia. For now, I'm going to remind you all to just go out and look up this long holiday weekend. We'll be back with a new episode on Tuesday when we're joined by Dr. Darby Dyer, who will be talking about her new research on Venus. For now, this has been the Daily Space.